Yes, good afternoon. So welcome to the webinar. So today we have Deepika from 5th SEM BSc PME, and she is going to give a presentation on differential equations. Deepika,
Yes, sir.
over to you. You can start.
Thank you, sir. Good afternoon, one and all. I am Deepika from 5th SEM BSc. I am here to present a webinar on the topic differential equation. Next slide, sir. These are my contents which I am going to explain. Invention of differential equation, introduction of differential equation, order and degree of differential equation, classification of differential equation, solution of differential equation, homogeneous differential equation, linear differential equation, and applications of differential equation. Next slide, sir. Now we'll know about history. As history tells, both the scientists claim to have independently invented calculus around the same time period. This is the key for calculus for literal development of integrals and derivation, set the stage for future mathematicians. These equations are invented by a physicist Isaac Newton and German mathematician Gottfried Leibniz. In the year 1671, Newton in rough unpublished notes by putting three types of differential equation. In the three types of differential equation, first two equations contain only ordinary derivatives of more dependent variable. Today, these are called ordinary differential equation. Wherein last equation containing partial derivative of dependent variable, it is known as partial differential equation. Both the terms are in modern. Newton finally published this equation in the year 1736 and he named as fluxions. In the same time period, that is in 1675, German mathematician Gottfried Leibniz unpublished notes and introduced the integrating symbol. Further, differential equation began with Leibniz, the Bernoulli brothers and others in the year 1680. Next slide, sir. Next picture, sir. These are the scientists who invented the differential equations, and these two peoples worked on the differential equation. Next, what is differential equation? An equation containing an independent variable, dependent variable, and its derivatives. Here, derivatives may be first order, second order, or higher orders. First, we know about independent variable and dependent variable. Suppose we have y equals to 2x plus 5. This is in the form of y equals to mx plus c, which is the equation of straight line. If I say for different values of x will give us different values of y. These are the two variables I'm taking in consideration. One variable is x and another is y. Now, if I have a function y equals to f of x, now different values of y may give us different values of x because y will be the function of x. Here, my x is independent variable because it is not dependent on y, and y is dependent variable because y depends on x. Now, let's see an example. In example 1, 2, and 3, all these examples containing independent variable, dependent variable, so it is a differential equation. Where in fourth example, it is not a differential equation because it doesn't contain any derivatives like dy by dx or d square y by dx square. Next slide, sir. Next, we know about two kinds of differential equation: ordinary differential equation and partial differential equation. Ordinary differential equation is nothing but whenever we are having only one independent variable, that is known as ordinary differential equation, and it is also known as ODE, and it is always denoted by D. And you can see the examples here. Both these examples are containing one independent variable. Next, partial differential equation. Partial differential equation means whenever we are having more than one independent variable is known as partial differential equation, and it is also known as PDE, and it is always denoted by though. And you can see the example 1 and 2 having more than one independent variable. Next slide, sir. Order of differential equation. Next slide, sir. Order of differential equation. Order means the highest degree of derivative appearing in differential equation. Now we know that there is first order derivative dy by dx and second order derivative d square y by dx square and so on. So the order of differential equation is the order of highest order derivative because in one differential equation there may be 2 to 3 participating derivative, which is the highest one that decides the order of derivative. Now let's see an example 1. In example 1, dy by dx is the only term and it is first order derivative. So the highest order of derivative is 1. Therefore, order is 1. In second example, d square y by dx square and dy by dx is the two terms. D square y by dx square, it is the second order derivative. So the highest order of derivative is 2. In third example, we have three terms in that. 4y triple dash is the highest order of derivative. Then highest order is 3. Therefore, order is 3. In fourth example, we have two terms in that d power 4 y by dt power 4. It is the highest order derivative. So the highest order of that derivative is 4. Therefore, order is 3. After knowing about order, next slide, sir. After knowing about order, we need to know about the degree because order and degree are the basic concepts of differential equation. Next slide, sir. Degree of differential equation. Degree of differential equation. Degree is nothing but power of highest order derivative appearing in differential equation. Finding degree is of two steps. First, we need to find highest order derivative, that means order. Second, should know the power of that highest order derivative, that gives us degree. Now let's see an example. In example 1, it has only one term, that is dy by dx. This is first step. we find the highest order derivative. Second step is power of derivative. In this example, there is no whole square or whole cube. Power is only 1, so the degree is 1. In second example, we are having two different terms. First term as 2 in order and second term as 1 in order. So we need to choose which is highest, 2 or 1. Here 2 will be highest. So consider d square y by dx square is the highest order. So the power of the derivative is 1. Therefore degree is 1. In example 3, we are having two different terms, first as 2 in order and second term as 1 in order. Here 3 is highest, so consider y triple dash is the highest order. The power of the derivative is 3. Therefore, the degree is 3. Where in fourth example, here d cube y by dx cube is the highest derivative, then its order is 3. The power of that derivative is 2. Therefore, degree is 2. Next, classification of differential equation. There are many types of differential equation and a wide variety of solution techniques. In that, we have linear differential equation and nonlinear differential equation. Under linear differential equation, we find the integrating factor alone, where in nonlinear differential equation, we find the solution by various methods. Those methods are separable method, integrating factor, homogeneous method, and exact differential equation. These are the methods to find nonlinear differential equation. Next, solutions of differential equation. In differential equation, we have two different solutions. One is general solution and other is particular solution. Now, what is general solution? It is a type of solution in which number of arbitrary constants are equal to order of differential equation. In this solution, there will be no particular values assigned to arbitrary constants. Next, particular solution. It is a type of solution in which specific values are assigned to the arbitrary constants. In a particular solution, particular values are assigned to the arbitrary constants, wherein general solution doesn't have a particular values to the arbitrary constant. So, specific values will assign to arbitrary constants will give us particular solution. Next, sir. Now, we'll go for example 1. In the example, we need to find general solution as well as particular solution. Here in this example, in general solution, we will get arbitrary constants. That constants will depends on order of differential equation. If it is second order, it will be two constants. If it is third order, it will contain three constants. Here in this example, y double dash plus 4y dash plus y 4y equals to 0. This is my differential equation. For that, I am getting a general solution y equals to c1 plus c2x into e power minus 2x, where c1 and c2 are the two arbitrary constants because here my order is 3. Where in the other hand, to find a particular solution, we need an initial values. After substituting the values for C1 and C2, we'll get a particular solution, that is y equals to e power 2 1 minus x into e power minus 2x, where it is followed by other two examples. Next slide, sir. Homogeneous differential equation. Next, sir. Homogeneous differential equation. If we have first order first degree differential equation, which can be expressed in the form f of x comma y divided by g of x comma y, where f of x comma y and g of x comma y are the homogeneous functions of the same degree, then it is homogeneous differential equation. And this is the example for homogeneous differential equation. Next slide, sir. Linear differential equation. Linear means the degree or power should be 1. Now, what is linear differential equation? It is an equation containing only the first order derivative, and the general form of that linear differential equation is dy by dx plus py equals to q. When we are solving the equation, first we need to compare with the general form, and it is in the general form, then we can say that the equation is linear differential equation. These two examples are linear differential equation, which is in the general form dy by dx plus py equals to q. Next slide. Now we are going to see about the applications of differential equation. We know that differential equation means the rate of change in the given system, and this concept is mainly used in science engineering, biochemical reaction, medical field, population growth, and spread of diseases. So, differential equations are absolutely fundamental to modern science and engineering. Most common use of differential equation in science is to model dynamical system. Now, first application is Newton's law of cooling. In this application, we are using ordinary differential equation. ODE means we know equation will be in the form dy by dx equals to f of x comma y. This is the first order differential equation. Now, second application is Newton's law of cooling. In this application, we are using ordinary differential equation. ODE means we know equation will be in the form dy by dx equals to f of x comma y. This is the first order differential
Deepika, you are not
equation.
audible.
Now,
Your voice is not audible. Sorry for the inconvenience. Just a few seconds.
applications. Now we are going to see about the application of differential equation. We know that differential equation means the rate of change in the given system, and this concept is mainly used in science engineering, biochemical reaction, medical field, population growth, and spread of diseases. So, differential equations are absolutely fundamental to modern science and engineering. Most common use of differential equation in science is to model dynamical system. Now, first application is Newton's law of cooling. In this application, we are using ordinary differential equation. ODE means we know that equation will be in the form of dy by dx equals to f of x comma y. This is first order differential equation. For example, take a cup of coffee. So initially it has a temperature of 30 degrees Celsius. If you put it in stove or in freeze, after 10 minutes the temperature may be decrease or increase. It depends upon the surroundings of a medium. Where we place the cup of coffee or a temperature, that means we put it in the freeze. After 10 minutes it will be decreases to 10 degrees Celsius. If we put it on the stove, it will be increased to 40 degrees Celsius. Now the statement says that the rate of change of temperature of a body is proportional to the difference between the temperature of a body and surrounding medium. Now, let the temperature of a body be T, surrounding medium temperature is T naught. Rate of change of temperature can be written in the form of dt by dt is directly proportional to T minus T naught. dt by dt is equals to plus or minus k into T minus T naught. Here, application is Newton's law of cooling. That means temperature should always will be decreases. So we can use minus k only. That means dt by dt equals to minus k. into t minus t naught, where k is a proportionality constant. By variable separable method, dt by t minus t naught equals to k into dt. If we integration of t minus t naught equals to kt plus c, t of t equals to t naught plus e power minus kt into c. Value of c may change and t will tends to infinity instead of 0. Here, my t is in a temperature of body and t naught is the temperature of the medium. Next slide, sir. And next application is exponential growth and radioactive decay, where following example describes several instances in science where exponential growth and decay in relative. Here I'm taking two examples. One is for exponential growth and other is for radioactive decay. Here my example 1. Consider in a colony of bacteria in a resource rich environment. Here resource rich means, for example, there is a plenty of food as well as space for the colony to grow. In such environment, the population P of the colony will grow as individual. Bacteria reproduce by binary fission. Assuming that no bacteria die, so that the rate at which population grows will be proportional to number of bacteria. So I can write it by dy by dt equals to ky. Here we consider the function y is the population p. So we can write in the differential equation in this type dp by dt equals to kp. That is the growth. So this k value is greater than 0. And this equation is known as growth equation, where k is a constant of proportionality. Here we know value of k is greater than 0. So here where k is a constant of proportionality, value of k is always greater than 0. So I can take the value of k equal to 3 per hour. It means that the individual bacteria cells as an average of 3 offsprings. Here P equals to P naught e power kt. This is the equation for the population of bacteria growing exponentially with time. Next, we'll go for example 2, and it is for the example of radioactive decay. Consider a sample of certain radioactive isotope here. We are going to take the value of k is negative. So if we have the differential equation in the form dm by dt equals to minus rm, in the special cases, we take the value of k is negative. We can write dy by dt equals to minus ry. Here y is the mass m. So dm by dt equals to minus ry into y is the mass m. So this equation is known as growth equation. Consider a second example, and it is the example for radioactive isotope. Consider a sample of certain radioactive isotope. Here we are going to take the value of K is negative. So we have the differential equation in the form dm by dt equals to minus Rm. In the special cases, we take the value of K is negative. We can write dy by dt equals to minus Ry. Here y is the mass m, so dm by dt equals to minus Rm. If we integrate the value of solution, m equals to m naught e power minus Rt. Here my m naught is the mass of the sample at a time t equals to 0. Next, we go for half-life time of a system. So first, what is half-life time? The rate of exponential decay is the half-life time. Given the decaying variable y equals to y naught e power minus Rt, where r is greater than 0 because r equals to k, that means positive numbers. So here y naught will be off life. So y will be equals to y naught divided by 2, where y naught is the initial state at y equals to 0. Thank you.
Thank you, Deepika.
Yes, sir.
Anybody has any questions? Any questions? Okay. Deepika, thank you. That was a beautiful presentation. So we will
Oh,
we will meet in the next webinar. Thank you. Have a nice day.